Good morning, dear audience. Me, along with my teammates Reese and Alex, will present our design assignment called Ultra-Wideband Ranging Evaluation. The IEEE 8022.15.4a standard specifies two ranging specifications, from which one is based on ultra-wideband communications. There is only one supplier on the market for this sort of devices, and it is called Decawave. The Decawave EVK 1000 is a complete single-chip CMOS ultra-wideband IC based on the 2011 ultra-wideband standards. It is the first in a family of parts that operate at data rates of 110 kilobytes per second, 850 kilobytes per second, and 6.8 megabytes per second. The resulting silicon has a wide range of standard applications for real-time location systems and ultra-low power wireless transceivers. To begin, our team had to define and agree on a set of real-world scenarios and document the tests performed there. Next, by using the specified data, the calculation of expected range with expected shadowing losses was conducted. A MATLAB simulation was created in order to estimate these values. After this, the following step was setting up an evaluation kit, the evaluation kit to examine, analyze, and explain the channel impulse response output of a pair of transceivers. After understanding how the Decawave works, these tests needed to be conducted in the scenarios previously chosen, and the comparison between the obtained results and the expected results was done. Following the guidelines presented earlier, the team decided on some scenarios that will test the device. The indoor scenario chosen was Alex and Reese's house, and the outdoor scenario was Alex's backyard. And we decided on some key points in the house that would be essential in the case the technology would be used for indoor appliances, but Alex is going to discuss about this in more detail. The device has two modes, anchor and tag, which can be set on the device by changing the configuration of the switches. In order to determine the absolute position of the tagged object, there are two implementation methods which can be used. The first one is the signal strength based scheme, which involves measuring the signal strength of the arriving radio signal at the receiver. This can be done by knowing the power at which the signal was transmitted, the propagation characteristics of the particular radio signal in the air, and some prior knowledge of the environment. This scheme is great in some circumstances, but not where a very high level accuracy is required. The other type of schemes are time-based schemes, which can be divided into time of flight, time difference of arrival, and angle of arrival. First, the time of flight scheme was simulated. Here, the time it takes for a radio signal to get from a transmitter to a receiver is calculated. Using the data, the physical distance between the transmitter and the receiver can be obtained because the value of the propagation of radio waves in the air is already known. So this is a picture of the time of flight scheme. P3, P1, and P2 are anchors, B is the tagged object, and R are the radiuses. Next, the communication between the transmitter and the receiver is unsynchronized, meaning that the tag and the anchor can exchange timing information, so the anchor can calculate the time of flight of the signal from the anchor without them being synchronized in time. The second scheme is the time difference of arrival, where three or more readers are positioned in known locations around the area in which tagged items are to be located, but the readers are synchronized in time with the others. This is a schema of the time difference of arrival. So P1, P2, and P3 are readers, and B is the tagged object. The third schema is called angle of arrival. It involves determining the angle at which the radio signal from the tag arrives at the anchor relative to the predefined directions. In this way, by measuring the angle of arrival at a number of anchors where position is known to the source of the transmission can be determined. This is a schema of these. So these are the angles we use to determine. But in the case of our project, the team has only conducted the time of flight scheme. Decawave describes the device as having a ±10 centimeter location accuracy across close distances and can range up to 50 meters, features that are not available on any other devices. The main application of this device would be in indoor environments, and it is proposed as an alternative to infrared and Wi-Fi technologies, since satellite-based GPS is unavailable indoors. Another great feature is the fact that it has the ability to carry signal through doors and other obstacles that tend to reflect signals at more limited bandwidths and a higher power. The technology used by these devices is a radio technology known as ultra-wideband that uses a very low energy level for short-range, high-bandwidth communications over a large portion of the radio spectrum. Ultra-wideband transmits in a manner that does not interfere with conventional narrowband and carrier wave transmission in the same frequency band, making it great for precision locating. The technology shows much potential in use for close range real-time location cases such as proximity detection, where the requirements are to determine the distance between two objects. You can use this in apps such as Find My Gadget around the house, or in a key hop technology so it can find your car in a parking lot. Now my teammates will take over the presentation. Alex is going to talk more into depth about the Decawave, and Rich is going to talk about the experiment itself and the analysis. Thank you. Alex?